So here's a quick video over momentum impulse. We'll talk about what it is, how it's conserved, and then a little brief discussion of the center of mass. Just like energy, momentum is a conserved quantity. What does that mean? It means the momentum I start with is equal to the momentum I end with. And what we want to do is we want to identify what momentum is, and that is mass times velocity. And then we want to identify what the momentum is before the collision and after the collision. And the reason we could say it's conserved is because all of the forces are shared between the objects. You just need to do the mv of object 1 plus the mv of object 2. If there's 3 objects, you do the mv of object 3, etc. And that would be equal to the amount of momentum, the m1 v1 f, if you will, plus the m2 v2 f, plus the m3 v3 f, etc. You can get into some types of collisions. The different types of collisions would be elastic, inelastic, and then sometimes people like to say the phrase perfectly inelastic. I like to think of them as they stick or stop, or do they stick or separate? And then is kinetic energy conserved before and after? So the most unique one is elastic. And typically with an elastic collision, you would have no loss of kinetic or mechanical energy before and after the collision. So in an elastic collision, we would say that not only is the momentum conserved before, but the kinetic energy before is equal to the kinetic energy after. For an inelastic collision, I'll put this pi equals pf as well, because that's a true statement. Only the momentum is conserved before and after. Sometimes they'll talk about a perfectly inelastic collision, and in a perfectly inelastic collision, they stick. So the momentum of the two objects become one object. It would typically look like a statement mv plus mv equals m plus mv. And then, so that's what you think about there. Momentum on its own wouldn't necessarily be a singular problem. You typically do some other things with it, but if you're going to have a momentum problem, you should probably be aware of a force versus time graph, in which case we identify that the force versus time graph is something is valuable. So we could draw lots of different shapes. We'll just draw a nice rectangle here. And in this rectangle, we can identify a few things like the area. And we can identify the area is force times time divided by 2. If it was a rectangle, it would be force times time. And if it's not any of these, then we can integrate our statement. And I'll show you that here shortly. Let's take a look at this a little bit more effectively. If I were to look at the force, I would say that it's a mass times acceleration. So it's a kilogram meter per second squared times a time. And then we would see that this is time. Oops, that's a second. And then this second and that second cancel out, and we're left with the kilogram meter per second, which checks out. Another thing that you can also look at here is that F equals ma. And if I take F equals ma, I break it down into its, I break down acceleration, how it's early defined in AP Physics 1 or in any physics class, as m delta v over delta t. And sometimes you would be doing a problem where you'd look at impulses, F delta t equals m delta v. I like to think of momentum as just being a tool that the Newton's second law lets us use. And in order to change the momentum of an object, you would need to have an impulse. I think of changing a momentum very much like work, changing energy. If this was an uglier statement like that, and we couldn't just necessarily do that, and it's pretty much fine. Instead of looking at it like that, we would say that our J, our impulse, which is equal to our change in momentum, would be equal to the integral of f dt. So we would need to know the function, and then we could integrate it over the bounds, initial time and final time. When two objects collide, the amount of force that they both experience is equivalent, but just in opposite directions. So the amount of impulse that each experiences is equivalent, but in opposite directions as well, because they both experience the same amount of force for the same amount of time. They can only be in contact with each other for so long. Momentum is pretty straightforward to me. It's just a conserved quantity. So if you're comfortable with energy, it should just be a relationship that goes along with it. Center of mass comes up as well, and that's just where the average mass would be located. I do an activity where my students take a meter stick and they move their fingers together and they identify that for a uniform object, the mass is right in the center. But what if I have an object here and then an object over here, but it's slightly larger? How would I identify where the center of mass is? So I need to pick a point and call 0. So we could say 0 is over here. We could say 0 is a lot of different places. But then what we would need to do is identify where on this number line would the center of mass be. So we would, if we said that this is 0, we would say that the mass, if this is position 0, and then we would identify maybe this is 1, 2, 3, 4, 5. So we got 1, 2, 3, 4, 5 units away. We would then identify, well, this has a mass of, let's say, 2 units, and this has a mass of 4 units. Where is the center of mass? How could we find this out? We must employ a formula, and that formula would be the sum of the mass times their distances divided by the sum of the mass. So in this case, that would be equal to the center of mass in the x. Notice this is horizontal. This works in the vertical and the in and out, the z dimension as well. So we have two objects, so I just do 2 times 1 plus 4 times 5 divided by 6. And then you'd identify that that's 20 and that's 2. I didn't pick the best numbers, so I did 22 divided by 6. And I find that to be somewhere around 3.3 2/3. And that makes pretty good sense. Why would that make sense? The center of mass should be closer to the larger object than it should be to the smaller object. You can also think of a torque type question if you wanted. If these were on a beam, where would I want the center to be? So I think the step that you want to be aware of is what could I name them? And you would have to name them. You'd have to pick a coordinate system. And then this is 3.6667, or 3 2/3 away from here. It's not necessarily 3 2/3 away from here. It's 2/3 of the way from there. 2 2/3 of the way from here. So I could have picked this as 0. I could have picked this as 0. They should have been worked out to be negative numbers. So something to keep in mind when you're doing center of mass. What's neat about using center of mass with momentum is if I have two objects, I don't know, let's say they're at rest, and I have a 2-unit object and that 4-unit object again, and they're both at rest. Right now they have a momentum that is equal to 0. And since the momentum is equal to 0 before, it must also equal 0 after. But what happens is that this object, the 2-kilogram object, will travel to the right, and the 4-kilogram object will travel to, or this 2 will travel to the left, and the 4 will travel to the right. Common sense and based on your experience, you would find that the 2 would go significantly faster than the 4, and to the left, then the 4 would go to the right. There's another proof that you could use, is you could say that since the center of mass of the system is is where it is, when they explode, the momentum of the center of mass is still 0 as well. So it won't move, meaning that this object has to go farther away. It has to go faster away than this one goes to the right in order to maintain that center of mass in the middle. What would be interesting to think about as well is if this system was traveling to the right at some and the system had momentum, and then there was an explosion inside the system. So we would say that the momentum before is 2 and the momentum after is also 2. But we would also be able to say that the momentum of the center of mass is also traveling where it would have originally, even if they didn't separate. I'm going to post a question for you guys to try out to look at that. But center of mass is just making sure that you have as much mass on one side as you do the other. And then the application that would be associated with momentum is that the two objects, if the center of mass, the momentum of the center of mass does not change because the forces are experienced the same. And you could think about it like this one would travel faster away from the explosion than this one because it has half as much mass. So it'll go twice as fast. So for every unit it'll go 2 units to the left for every amount that this one goes. For every 1 unit, this one goes to the right. But 4 times 1 is equal to 2 times 2, so the center's still right in the middle of the two objects. So that's something to think about if you're looking for an application of momentum in the center of mass. Of course, you would talk about a problem with something rolling off and potentially landing on something, forming a perfectly inelastic collision. Or you could think of a collision taking place, causing a pendulum to move. A ballistic pendulum is a very common example. But the beginning of that problem, if you see the phrase collision, is PI equals PF. And then from there, you can either use conservation of energy, you can use some simple harmonic motion statements to identify the period, or not the period, but the amplitude of the motion. But ultimately, this would be a part of a larger question. And then I'll post some momentum questions for my students to take a look at as they prepare for the AP exam. But momentum is a conserved quantity. It is a great place to start any problem. And have a wonderful day.